Guys, welcome back to another breakdown. I've said that so many times from all these breakdowns, but you know what? I like it, so I'm gonna keep saying it. All right, here we got a CP passage. All right, we got some, what is this? Got some organic chem, some gen chem we're looking at, all right? And yeah, guys, I'm gonna show you guys exactly how to pick the best answer choice, how to highlight, how to read the passage, basically how to get more questions right on your MCAT. That's what I'm going to show you how to do in this video. So before I go ahead and break this down and answer these questions, guys, do it on your own first and then write down, your answers, write down where you kind of thought it was confusing, any type of mental process that you're like, oh, I was stuck here. All right, write that down. Look at your weaknesses and fix those weaknesses so you can optimize yourself and get the best score. All right, so pause it whenever you need to. I'm going to scroll down here. Okay. This is the first question. This is 49, 50. Ooh, organic chem, nice. 51, 52. All right, guys, so I'm going to break it down right now. A prodrug must undergo chemical conversion in the body before becoming an active pharmacological agent. All right. The metabolism can occur in the stomach before absorption takes place in the blood or even in the target tissue. Okay. So I'm going to highlight this where metabolism can take place. Blood, stomach, target tissue. Cool. The prodrug acetaldehyde, I think I said that right, is absorbed in the duodenum and then undergoes acid catalyzed hydrolysis of its acetyl functional group to become an active metabolite. Okay, I'm going to highlight acid catalyzed hydrolysis because I know that from my content review. All right, and I'm also going to highlight this here because I'm making a mental note in my head. Okay, when you highlight, you kind of remember little things better. All right, and so I'm remembering acetaldehyde undergoes acid catalyzed hydrolysis. All right, of what? Of its acetyl functional group. Okay, cool. Para substituents. You guys should know para, ortho, and meta. Okay, you should know that. Para substituents on aromatics can influence the relative stability of carbocation intermediates and impact the rate of acetal hydrolysis and acetaldehyde efficacy. I'm not going to highlight here because I know from content review that carbocations can be, deactivated, activated depending on what the substituent is and depending on the place of the substituent. Okay. To investigate the role of para substitution on the stability of the acetaldehyde carbocation intermediate, a chemist used isodesmic reactions to determine the relative stabilization energy for various substituents. Okay. To test the stability, all right, they used whatever these are called, isodesmic reactions, all right, to look for the RSE, the relative stabilization energy. Okay, I'm highlighting this. I do not know what this is, so I'm going to highlight it, and they're probably going to tell me what it is right now, so I got to pay attention here and lock in. Isodesmic reactions are reactions in which the type of bond broken in the reactant is identical to the type of bond formed in the product. Okay, it's way more simpler than I thought. Okay. RSE provides a mean of measuring the difference in the energy needed to form the cation as a result of the presence of a given substituent. All right, so RSE, what is that? That's the difference in the energy to form the cation as a result of the presence of a given substituent. So it tells me how stable this cation is. That's what it tells me, depending on the substituent, okay? It allows me to compare different substituents based on the energy, Equation 1 shows the isodesmic reactions involving the acetaldehyde carbocation used to calculate the RSE for a substituent labeled X. All right, and I'm not looking at the figure, only look at the figure when the question asks for it. Okay, we don't want to waste time on that. The chemists evaluated the effects of 5 different substituents at position X. For each compound, the heat of formation was calculated for the substituted neutral compound and cation X and X plus. Okay, heat of formation. You should know what that is. Okay, that involves a bond breaking, bond forming. All All right, exothermic, endothermic, you should know that. Substituted neutral compound, so that is for the X, and then the cation corresponds to X plus. All right, respectively, along with the non-substituted neutral compound. So H is the non-substituted one, the regular one here. All right, and the cation for that is H plus. Okay, we got some things to remember here. I'm probably going to be going back and looking at it, so it's okay. The change in heat of formation from H to H plus, okay, from the non-substituted to the cation, and X to X plus from the substituted to the cation, gives the energy required to deprotonate each compound. And the difference gives the RSE. Okay, so the RSE is that difference. All right, then they give us a figure here. RSE based on the change in the heat of formation. Okay, RSE is the stabilization energy. The heat of formation, energy required to deprotonate, and RSE was calculated for each compound and recorded in Table 1. Table 1, identity of substituent X, heat of formation, deprotonation energy, and relative stabilization energy for each compound. All right, this passage gave us a lot of information. They threw a lot of information at us, this new technique here. What's going on here? Okay, we're going to find that out. I would say this passage is medium difficulty, medium. All right, but the questions are easy. The question is the easy part. The passage is the little tricky part. Okay, that's what it is. These questions are way easier than you guys think, guys. You're just overthinking. All right, which of the following cations will form most quickly from loss of a hydrogen atom? All right, so we have to look at the energy required to form this cation. All right, and they should have said according to Table 1. That would help. All right. Okay, let's see. What is this? What is this here? Well, this is the X plus, I believe, right? That's what the substituent with the cation is. Let's double check here. Substituted neutral compound and cation. So X plus. That's the X plus. All right, and this is formed from loss of a hydrogen atom. So this is going from the X to the X plus. Okay, the X was this, and then we lost the hydrogen atom, so we became the X plus here. Okay, X plus matches. This is the substituent, the X, and the plus is the cation here. Okay, so we're looking for the energy required to make these. So X to X plus. X to X plus here, the delta H for the X to the X plus. Okay, and they give us the energy required. Okay, cool. Now you have to make the distinction. You have to assume something, okay? Your assumption should be from your content review. This is what they want you to assume, okay? They want you to assume that when you require a lot of energy to go from X to X plus, that will mean that the product is stable, okay? If you use only a little bit of energy going from X to X plus, that would mean that the compound is less stable, but it would also form quickly, okay? Little energy to go from X to X plus equals quick forming unstable product. Lots of energy going from X to X plus equals longer taking product, a longer process to make the product, and also more stable. Okay, you should know that from the what's it called? The thermodynamic versus kinetic product. Okay, I'm just gonna look it up here so you guys can remember it. All right, remember kinetic forms quicker and it's less energy. So this one here, okay. Look, kinetic, intermediate, transition state. All right, oh, this way. Okay, so kinetic here, here. So we're starting, and here's the kinetic product. We only required this amount of energy, whereas in the thermodynamic product, we require way more energy. Okay, more energy, more stable product. Less energy, less stable product, but it's going to be faster. So the question is asking for one that forms quickly. Something that forms quickly, Okay, it's going to go fast and it's going to have the least amount of energy. So which one has the least amount of energy here? CH3OH, which is 181. CH3, 185. F is 191. And H is over here, 188.2. The one with the least amount of energy is going to form the quickest. And the one with the least amount of energy is OCH3. So it's this one. Answer is A. I'm confident in my answer choice. That's actually a really good question. Okay, I like it because it involves you to go back and make assumptions and look at the table. So that's pretty MCAT representative there. What is the correct order of the 5 para substituents on the carbocation intermediate if arranged from most stabilizing to least stabilizing? All right. They told us in the passage to determine if something is least to the most stabilizing, looking at the para substituents, they told us to look at the RSE. Okay. So I'll tell you where they told us. They told us over here. Okay. To investigate the role of para substitution on the stability of the carbocation, a chemist used isomer reactions to determine the RSE. Okay, so the RSE determines the stability depending on, do we have, what type of substituent do we have? All right. So the RSE we're looking at, and they give us this over here. All right, so here's the RSE. So most stabilizing to least stabilizing. So another assumption has to be made. All right. Does more RSE equal more stabilizing? Or does less RSE equal more stabilizing? All right. A lower RSE means more stable. Why? Because the RSE is negative. Okay, the RSE is a difference. So look over here. You have H plus to H, then X to X plus here. From here to here is more negative. From here to here, it's positive. Moving up. The difference between those is a negative number. It's a negative amount. And that negative amount is related to the heat of formation. All right, and a negative heat of formation is exothermic. If it's exothermic, that means energy was released. Okay, we formed the bonds and that extra energy was released. All right, if it's endothermic, we need energy to make the bonds. All right, so an exothermic product would be more stable in this case. So the more negative, the more stable. All right, so the most stable is going to be the NO2 because it has negative 260. And then next, it's going to be the negative 6.3. And then the negative 2.8 and 0.1, 2.9. So the most stable is going to be the NO2 substituent, followed by OCH3. NO2, OCH3, and then CH3. So this one, answer is C. Let me know in the comments if you guys have any questions about that. That was a pretty hard question because it required you to really think and say, hey, high RSE or low RSE means more stable. All right. Remember, just because something is high, it doesn't mean it's more stable. You have to look at what the definition is of that word. What are we looking at? Question 50. During the experiment, scientists noted that several of the reaction beakers became hot to the touch. All the final reactions could cause this result except what? Great question again. This is a really good passage, guys. This is very MCAT representative here, okay? So if it's hot to the touch, what does that mean? It means we release energy. If we release energy, that means it's exothermic, okay? So we're looking to find one that is not exothermic, all right? Hot to the touch, released energy, it became hot. Let's look at this one here. Is this reaction exothermic? All right, so we have substituent and the carbocation here. So which one's this one? This is X plus, I think. Let's check. All right, we have substituent, carbocation, substituent, carbocation, that's X plus. All right, and we're starting from the X here. Okay, so the X to the X plus, what is the delta H for that one? That one is positive. Oh, hold on. The delta H for X to X plus is positive, 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 negative, Is this X plus or is this H plus? Because this is telling me that all of them are exothermic and this one is, this column is telling me all of them are endothermic and this one's exothermic. But the question is asking me for which one is endothermic. We can't have 3 of them endothermic. So is it X plus or is it H plus? It's not. Good question. Very good question. Very good question here. Okay, let's see. This one sticks out. This is the odd one out. All right. All of them are positive for this one. And this one's the only negative. So that gives me an idea that this one is correct. All right, remember, the one that sticks out of all of them is usually correct, even though I'm not 100% confident in this. So let's look. This is the X plus. This is X plus. This is the X. This is X. And this is X. What about the formation of X? Formation of X here is endothermic, and the rest of them are exothermic. So this is the one that stands out, and if I don't know whether to use this one or this one, but this one's the one that stands out for both times. So using test taking strategy skills, which is going to be on the MCAT. Okay, you're not going to look at every passage, every question, and be excited and know the answer 1,000%. Okay, you have to use process elimination sometimes, and that's fine. Okay, I'm an MCAT tutor and I use process elimination sometimes. So I'm gonna go with D. D is the best answer choice. What effect will the addition of a fluorine substituent have on carbocation stability? Great question. Very, very great question. I love this passage so much. Okay, high yield organic chem question right here. All right. I'm going to have to use a whiteboard for this one because I really want to explain it to you guys. All right, the answer, I'll tell you the answer right now if you want to skip my little lecture here. Fluorine's going to be destabilizing it because, all right, the answer is A. All right, if you know this already, you could skip my little lecture, but if you want to learn and really understand it, listen up, guys, okay? So I need the whiteboard, this whiteboard here. All right, let's move over. Okay, say you have a carbocation. I'm going to teach you guys electron withdrawing groups, electron donating groups, stability of the carbocation, all that stuff right now. Okay, I'm going to do it in like 1 minute. So say you have a carbocation. Okay, so you have carbocation right here. All right, and you have a position here. Substituent is fluorine. All right. Fluorine is electronegative. You look at the periodic table, it's electronegative. It's an electron withdrawing group. It withdraws electron density away from the carbocation. So if it's electron withdrawing, it's going to bring that electron density up here. All right. Does this mean activation or deactivation? Does this mean stabilizing or destabilizing? That says destabilizing, all right? What does that mean if we have an electron withdrawing group on this carbocation? Does that mean activating or deactivating? Does that mean stabilizing or destabilizing? Well, this is how you find out. Use your common sense here, okay? If I had an electron donating group, okay, like a alkyl chain, let's say, on this carbocation, all right, electron donating group would get that electron density and donate it to the ring. If I'm donating it to the ring, I now have a positive from the carbocation here and the negative charge close to each other. Okay. This negative is coming from the electron donating group and this positive is from the carbocation. Okay. If I have a negative and positive close together, that's stable. Okay. Positive and negative are stable when they're together. So if I have an electron donating group, it stabilizes the ring. Opposite for fluorine. If I have an electron withdrawing group, I'm not going to bring that electron density towards the ring. I'm going to withdraw it. I'm going to make electron density go away. And now I'm separating these two charges. And when I'm separating them, there's going to be more energy. there's more energy, this is going to be less stable, and I'm destabilizing the ring with an electron withdrawing group like fluorine. All right, makes sense? Cool. Any questions? Comment down below. I'll be answering it. Fluorine group will be destabilizing because highly electronegative. Answer is A. The reaction produced the X form of compounds 1 to 4 from standard state elements will be spontaneous under what conditions? So X form from 1 to 4, which one's the X? This is the X from 1 to 4. All of them are negative. We have a negative delta H. All right. And they're asking spontaneous or non-spontaneous. Okay, we're going to have to use Gibbs free energy here. All right. Delta G equals delta H minus T delta S. All right. Delta H has got to be negative because look at them. They're all negative here. All right. So this one's negative minus the temperature. They're asking us, should we get high or low temperature? So we leave a T here. Delta S, okay, delta S, is that going to be negative or positive here? Well, we're going from standard state elements to compounds 1 to 4, which are with the substituents. Okay, that's the ring with the substituents here. We're going from standard state, which are like the N2, O2, this is and here. So like an N2, an O2, what else here? Like a CH3 maybe. You know, those that are stable, but they're small. They're small and more in number, and they form one compound. So the entropy is decreasing. Okay, the entropy is decreasing. We're going from a disorder to a more orderly state. And when we do that, entropy decreases. So delta S is going to be negative here. All right. And we're assuming, we could assume spontaneous or non-spontaneous. Let's look at the answer choices. Let's assume spontaneous because there's more answer choices saying spontaneous to make our lives easier. So I'm assuming spontaneous here. All right. Does this T have to be a high number or a low number to make this spontaneous? Let's find out. All right, we have a negative here. We have a double negative here. All right, so these are going to cancel out and become positive. And then we have a T here. I'm going to put value. Okay, like should it be a high value or should it be a low value? And it's going to be equal to something spontaneous here. Now now it makes a little more sense here. Okay. Negative plus a big number or negative plus a low number gives me a negative product. All right. A negative plus a low number will give me a negative product. All right. I remember this, but you can plug in numbers if you want to be safe. Okay. So let's say we have negative 100, negative 1,000 joules, let's say, plus a low value. So like, let's say a 200 joules. All right, 200 joules. That's a low value, lower than this. Now, negative 1,000 plus 200 joules is going to be negative 800 joules, something that's spontaneous. Negative. If this was instead like 20,000, all right, the value would be high from a high temperature. Then you can look at this negative 1,000 joules plus 20,000 joules, and you can easily say that that's going to be a positive number. All right, that's going to be positive 19,000. So we want a low temperature here. All right, you can remember the table for these. You can put it to memory and say, oh, negative delta H plus negative delta S gives me blah, blah. You can remember it, or you can do it my way for every time you encounter a problem like that on the exam. So reaction will be spontaneous at low temperatures, 52 is C. And that is it for this, guys. Now let's see if we got all these questions right. Remember, I do this live for you guys right on the spot. So let's see. 48 is A, and that's the explanation. 50 is D, that's explanation. 51 is A, that's explanation. And this one is D. We got all of them right. So that's it for this one, guys. Comment down below. Let me know what you guys think. This is a great passage, and I hope you guys watch this video for the entirety because you can learn a lot from these types of passages. All right, it's a blueprint exam, and I'll see you guys in the next video.